Okay, so one of the things that Wilson would be able to tell you is how physics changes as you change the scale. Basically, every time you integrate out a new shell of high momentum modes, you see how the couplings and masses change. So that's something interesting that we would like to learn about. But in our description, it's not very easy to do that. And it's basically because we took the cutoff lambda to infinity. So we don't have that as a physical scale anymore. It's been removed from the theory. So we might ask, is there another way to study how parameters of the theory depend on scale? And well, yes, there is. So what you should remember is that in the Feynman-Schwinger-Tomanaga way of thinking, in the Feynman-Schwinger-Tomanaga way of thinking, you must define all physical parameters. So physical parameters. And remember, if you ask Wilson what are these physical parameters, he would say that they are the set of marginal and relevant couplings. So those are the physical parameters, the marginal and relevant couplings. We must define these physical parameters by a matching condition, or this is often also called a renormalization condition. Okay, so for example, you remember when we wanted to define the coupling, we did that by studying the 4-point function that had its legs amputated, the connected piece of that at some specific kinematic point. So what we can do now, so Feynman-Schwinger and Tomanaga told us we must define these physical parameters, and we've discussed how to do that. Now, here's a little twist coming from Wilson, or the Wilsonian way of thinking, I should say. So our matching conditions or renormalization conditions can be imposed because we're just using them to define these parameters at any scale. Let's say M. Okay, so we can choose to define our physical couplings and masses at any scale M. Now, here comes the point. I might decide to define my parameters at a scale M1. And you might decide to define your parameters by doing your matching, your normalization at scale M2. Well, if you and I are going to agree on physical quantities that we calculate, then we're going to need to set our parameters to slightly different values. So here now is an important question. Let's maybe put it in blue just to have it stand out a little bit. How should parameters of the theory be adjusted so that two observers doing a matching or a normalization, so I'm going to say matching at different scales, agree on all physical observables. Okay, so that's the question. How should the parameters of the theory be adjusted so that two observers matching at different scales agree on all physical observables? So this is the key question that we want to ask. The Cullen-Samanzik equation is exactly the equation that tells us how to do this. It tells us how to adjust the parameters so that correlation functions computed by two different observers agree. And in this way, we learn exactly how parameters depend on scale, even though we're thinking in the Feynman-Schwinger-Tomonaga description, where we've taken the cutoff to infinity. So we've lost the scale defined by the physical cutoff of the theory, because we've taken that off to infinity. But the way we put it back in again, we do the matching or a normalization at a specific scale. Okay, let's now derive the Cullen-Samanzik equation. So let's say derivation of Cullen-Samanzik equation. Good. Okay, now I'm going to make a simplifying assumption. I'm going to put all of the masses equal to naught, okay? And this is done for simplicity. You know, we could relax this. Then we would need, in addition, to discuss how the mass terms are normalized. This involves some discussion of composite operators. It's not too difficult, but I'm not going to do it here. I just want to have the simplest possible description. So I've said m squared, our only relevant parameter, equal to 0. Good. And then what we will do is Cullen-Samanzik starts off by considering a correlation function. So let's call our correlation function Gn. So it's going to be an n-point function. It will therefore be a function of n coordinates, n space-time events, x1, x2 going up to xn. And let's just think about what we're doing. So one way to think about this quantity is we're taking the vacuum expectation value of the time-ordered product of n physical fields. Okay, this is definitely something physical that an observer may wish to measure. And remember, we can write this as the wave function in normalization, z to the minus n over 2, and then we replace the physical fields by the Baire fields. So the physical field, this would create a particle with probability 1. So let's maybe just remind ourselves. So this creates a particle with probability is equal to 1. These fields, these create a particle with probability less than 1. So they're not the physical field. Okay. Now, if we take a look at this Green's function, so what are we interested in doing? Well, we want to change, we will change m into m plus delta m. And so we'll make that change and ask for the change in the correlator, delta Gn. So we'd like to know what the change in the correlator is under a small change of our normalization scale. So let's try to figure out what depends. What are these quantities? What do they depend on? Well, this piece of this factor sitting over here, that's just a correlation function of the Baire fields. We have not used any matching condition to define that. We just computed it straight away using the Baire Lagrangian. So this is the thing that's going to depend on the Baire parameters. So let me write G there. It will also depend on the cutoff lambda. One thing it's not going to depend on is M. And it won't depend on M because nothing that appears in this factor actually has used the matching conditions. Okay. In contrast to this parameter Z sitting over here is fixed by a matching condition. So you might remember that what we found before when we were working at one loop is that Z was completely fixed by the requirement that the 2-point function had a pole that was equal to I. So it was fixed by a matching condition. So this factor over here, Z, this will depend on M. So there's M dependence inside Z. It's all sitting inside Z. So now, what we would like to calculate now is how will the Green's function change? Okay, so if we look at that Z to the minus N over 2, well, Z to the minus N over 2 is a multiplicative factor. I take products of a whole bunch of these, one for each field. I don't want my changes to be multiplicative. I know they're going to be additive. So I know from the get-go that it's better to talk about changes in log Z instead of changes in Z. So it's much better to think that the log of Z goes into the log of Z plus the change in the log of Z. So then Gn, which is equal to e to the minus n over 2 log of Z times by this correlator that doesn't change. It doesn't depend on the normalization conditions, so it doesn't depend on the scale M. So that stays fixed. So if we change the scale M, the only change that we'll find is inside the log G. So in exactly the same way that M goes to M plus delta M, Gn goes to minus n over 2 log Z plus delta log Z, and then this correlator that doesn't change. And we know that this has to be equal to Gn plus the change in Gn. Okay, we will continue in a moment.